I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this video where we are understanding the mechanism behind why this works, the L Hopital's rule. Students will frequently see an indeterminate limit form and then in a robotic manner automatically apply the rule. They won't understand why it works. These are the questions that we need to answer. Consider that you have an indeterminate form, let's say infinity over infinity. We know we'll do the derivative of the numerator, derivative of the denominator, and then we'll see if the indeterminate limit form has changed or not. And then we'll see what the result is. But why are we doing derivative? Why aren't we doing integral? Why are we not doing another procedure? Why is it always just the derivative of numerator, derivative of denominator? These are the questions I want to answer for all of you here in this video. To best appreciate the reason or the mechanism behind this rule, it is important to look at that indeterminate form which is of this type, infinity over infinity. You can certainly do it for the other forms, and there are, but this one right here will give you the best appreciation for why the rule works. And I will show you by means of two examples. Look right over here at a specific case, limit as x approaches infinity. We have a specific function here on the top. We will call that e to the x. I have another function here on the bottom. I'll call that x. Case A and then case B. Two examples will be used to understand the mechanism behind this. X divided by e to the power of x. You can see the difference between the two functions. They're rational functions. Case A and then obviously case B. When you're looking here at case A, you put infinity in places of x. What do you have? E to the power of infinity divided by infinity. In essence, you're looking at infinity over infinity. The same would happen with regards to case B. Why do we start thinking about L Hopital's rule when we see something like this? We are looking at infinity or infinity. We don't know the extent or the quantity or the quality of these infinities. We know in essence we're looking at infinity or over infinity. The reason why you want to start thinking about the L Hopital's rule, or the reason why it works, is because it helps you solve the tug of war that's occurring between these two independent infinities. Do not think of this as a unifying item. There are two specific infinities, one coming here in the numerator, one coming here in the denominator, simply because we have two different functions. We had an f function and a g function which comprised a rational function. There's a tug of war going on between these two. Which of these function giving rise to the infinities is winning, or which one is pulling the other function towards itself? The essence of the question that we need to answer is which of these functions is approaching or arriving at infinity faster than the other. Now, the only way you can answer that question, and the reason why the L Hopital's rule works, is because you have to start thinking about this very important concept, which is the concept of rate of change. Why is it that the derivative gives you a rate of change? Because it's telling you at a particular point what that rate of that function is. That's a question which needs to be answered, which is why then we end up start doing derivative of the numerator and derivative of the denominator, polynomial or expression or function, however you want to call it. It is the rate of change calculation which brings this tug of war to an end. And look, when I do the derivative, in this case A, of the numerator, I have ending up with e to the x. When I do a derivative of the denominator, I'm ending up with 1. The derivative of this is 1. Now look what has happened. You've gone from an exponential function, a parental exponential function, to you can say a offspring function. Its derivative is just e to the x. You started with e to the x, you ended up with e to the x. Look here at the denominator. The parental function was y equals x, which you know to be a line which looks like this going through the origin, having an equal steepness, equal flatness, slope here is equal to 1. But when you did the derivative of this, you ended up with a horizontal line, y equals 1. You want to call it that, we can, but what is the slope of this? It's equal to 0. Now when you're looking at the exponential function, the rate of change, you can imagine what the rate of change of an exponential function would be. It would be certainly much higher than this and much higher than this. The rate of change of this at any point is much higher than either of those. And then now you see why the rate of change calculation is important. It brings to end that discussion or the debate or the tug of war between these two. Which one wins? Exponential wins. This one loses out because its rate of change is considerably less than that. Which one is approaching infinity much faster than the other? This one is approaching infinity much faster. Hence, when you look at this particular expression or this limit through the L Hopital's rule and then you apply the infinity, what happens? You're looking at e to the infinity over 1. Your end result of this outcome must be infinity, and it's right. Because in this tug of war, the numerator expression or the polynomial or the function won, the denominator lost. and the rate of change calculation was needed to bring that debate to an end. So that right there is case A, and it clearly shows why a rate of change calculation is needed, which is why the L Hopital's rule has a rate of change calculation built in it. The end result from this limit for this is an infinity. We'll just mark it over here. Now look right over here. Case B, what do we have? When we put infinity in places of x, we still have this indeterminate form play out. So now we are thinking about the L Hopital's rule, because there's a tug of war going on between these two. Which one is winning, which one is losing? You do the derivative of the numerator, you end up with a 1. You do the derivative of the denominator, you end up with x. In terms of rate of change, which one has won? This has won. This has more weight to it because it's approaching infinity by means of its rate of change much faster than this function right here, which has given you a 1, a horizontal line with a rate of change equal to 0. Here the rate of change was equal to 1, here it's equal to 0. But the rate of change calculation, that is your derivative calculation, brought that tug of war or the debate to an end. And now when you do your completion, you no longer have an indeterminate limit form, but when you do it, you're looking at 1 over infinity and you're looking at 0. The end result of this limit is 0. But it was enabled and made easy by means of the L Hopital's rule, rate of change calculation. And that right there is in essence why you have this derivative procedure built in it. Again, I'll tell you, it simplifies or it solves that debate we have. There's a tug of war going on between the numerator and the denominator expression. Each one is approaching infinity at a given rate, but which one is approaching faster? And that one will dictate the limit outcome. Here, this is approaching faster, hence infinity is our outcome. Here, this is approaching obviously faster. Our outcome is 0 because you end up seeing 1 over infinity and it zeroes out. So we're good. If anyone were to ask you why the L Hopital's rule has a derivative calculation in it, because you need the rate of change to help solve that tug of war going on between the numerator and the denominator expressions. Well, that's it for this video. I hope you enjoyed it. Thank you. Have a good day. Bye.